So we got a related rate problem. We got to do some time problems again. Gravel is being dumped from conveyor belt at a rate of 30 cubic feet per minute. Its coarseness is such that it forms a pile in the shape of a cone, whose base diameter and height are always equal. So the diameter and the height are equal. They show it in the figure there. How fast is the height of the cone, height of the pile, increasing when the pile is 10 feet high? All right, first thing, again, how do we tell this is not optimization? Right there, all right? That's how we tell it's not optimization. So immediately we should be able to write this. And again, known and unknowns in my class usually are worth 10 points out of 40. It's a quarter of the score. 30 cubic feet per minute. So dVdt, right down here, equals 30 cubic feet per minute. Alright? So we know that. And we also know that the pile has the diameter and the height the same. Okay? I don't want to think of this as diameter, obviously, though. I know that right away. Because I know that the volume of this cone is going to be based on the radius. So I'm going to think of it as R and R. Okay? 2R is equal to H. And I'll even write that at this point, that we were given 2R was H. I don't want to deal with another variable in the diameter. We remember from geometry that the volume of a cone like this is 1/3 pi r squared h. Area of the base is a circle, pi r squared. That height is the height, and the third is because it goes to a cone point. So we have the volume, which I don't need to see, so I could write volume equals 1/3 pi r squared h. I could take the derivative of v right now, right? It has two variables, r and h. I could do the product rule, right? And the derivative of r squared is 2r dr dt. Derivative of h is 1 dh dt. But the problem here is I don't have much information, and what it asks to find is just dh dt, right? So dh dt when the height is 10 is what we were looking for. So there's the information. That's all the stuff the problem gave us. And we have to look at all this now and say to ourselves, do I want to differentiate this right away? Do I want to get rid of a variable? Again, when we can, we almost always want to get rid of a variable. I want dh dt. So I would really like to get rid of r, because this is what I want to find. To change how fast, that's the key word, how fast is the height of the pile increasing? So I want to find dh dt when the height is 10. Alright, so I want to get rid of r. And I see from my relationship the diameter and the height were the same. That means the radius is the height divided by 2. So I am going to do a substitution here. And I'm going to take my green thing and my blue equation. I'm going to write a new equation down here of volume equals 1/3 pi h over 2 squared h. And I'm taking some time here because this is one of the most common errors. I see 1/6 all the time. It's not 1/6. 1/2 times 1/2 inside the square is 1/4. 1/4 times 1/3 is 1/12 pi. H squared h is h cubed. And what we've developed here now, all right, is a formula that tells the volume of this pile just based on the height, knowing that the pile's diameter and height are the same. And now I look at this and say, okay, if I take the derivative with respect to time of this, I do implicit differentiation with respect to time, I know the derivative of v is dv dt, 1 dv dt. I know the derivative of h cubed is 3 times 1/12 is 3/12. Pi stays. H squared, but then we did derivative with respect to h, and then again with respect to time. And then we come down and we look at the equation. There are 3 unknowns, but we know 2 of them. We know how much gravel is coming up the conveyor belt per minute. We know where we want to find the change in height. So 2 of those are going to disappear. 1 equation, 1 unknown. Find a freshman, it's algebra 1 time. Alright? dv dt, 30 cubic feet per minute, equals, I'm going to change 3/12 to 1/4 pi 10 feet quantity squared dHdt. Again, I can see the units work out, but I'm going to write them out to make sure we all see that they work out. 30 cubic feet per minute. 1/4 pi 100 feet squared is what we should see here. 1/4 pi 10 times 10, right? 100 feet squared. A fourth of 100, I think, is 25 pi. Feet is feet squared, dHdt. And I'm going to divide both sides right now by 25 pi feet squared. Feet cubed divided by feet squared is feet per minute. That's good. 30 divided by 25 pi. I'll just wait and reduce it here in a second. Or not reduce. Probably I want to use the word simplify. So the answer for this problem today, dHdt, is 6/5 pi feet per minute. And again, I sit here and I don't like that number. I mean, it's exactly the answer, right? But I sit here and I think 6 divided by pi is basically 2, you know. 2 divided by 4, or 2 divided by 5 is about 0.4. So guys, this is growing 0.4 feet a minute. It's growing about half a foot a minute. So as you're pouring a lot of gravel, for lack of a better way to say it, a cubic yard of gravel, right? 30 cubic feet. That's a big pile. It's just, the pile's just growing 6 inches every minute. All right? So if you had to carry it away and do stuff like that, this would be part of the related rate. All right? And again, the hardest part here, I think, is way up here. I think once you get to the calculus from here down, it's not so bad. All right? It takes practice setting up problems.